In this second video on cylindrical coordinates, we will focus on integrals. We will start directly where we left off from the previous video, so make sure you watch that one first. Here, the main focus will be on cylindrical coordinates, but I will mention the equations for general orthogonal coordinates as well. Let's do a quick recap of line integrals in Cartesian coordinates first. Assume that we want to integrate the function f of r over a curve C. The line element ds will have the same direction as the curve C. In Cartesian coordinates, we would describe the line element by dx in the x direction and dy in the y direction. Hence, we can write ds as dx x hat plus dy y hat. We can separate the integrals as one integral in the x direction and one in the y direction. To solve a line integral, we need a parameterization of the curve. Assume that x and y are given by the parameter t. We can now multiply and divide by dt, which gives us the expression we use to solve line integrals, assuming that we know x of t and y of t. Now, what if we instead have the curve given in polar coordinates? In polar coordinates, we would have the following unit vectors, which would be changing along the curve. Now, let us use these to describe the line element ds. The radial part will simply be the rp. When we use the small step in the phi, however, we know from the expression of arc length that the part in the phi direction will be rp d phi. Hence, we can write a small step ds as drp hat plus rp d phi hat. Now, let us replace the expressions in the curve integral with the expressions in polar coordinates. Instead of x, we use rp. And instead of y, we use phi. Note that as ds is rp d phi hat, we need to insert an extra rp here. If we have cylindrical coordinates, we would simply add dz z hat to the line element. When you solve the line integral, be careful that rp hat and phi hat change direction along the integral. I will show examples on how to handle this later. Now I am going to take a step back and talk about the general case for how to find the line element ds. Let us demonstrate it first with the Cartesian coordinates. Write ds in Cartesian coordinates. ds is just a position. Hence, we saw in the previous video that x hat is the partial derivative of the position with respect to x. And y hat is the partial derivative of the position with respect to y. For now, we can drop the parameterization dt. Note that the expression for ds simply is the chain rule for partial derivatives. This idea will work for any orthogonal coordinate system. Replace x and y with u1 and u2. Multiply and divide by our scaling factor h. Remember, we need a scaling factor as the partial derivative only gives the direction of the unit vector. But it may have a different length than unity, as we saw for the phi derivative. Now we can replace 1 over h1 ds du1 with the unit vector u1 hat. And 1 over h2 ds du2 with the unit vector u2 hat. And place the unit vectors last. If we have 3 dimensions, add a similar term for u3. This is the general expression for the line element ds, which will work for any orthogonal coordinate system. You can compare it with the expression for cylindrical coordinates, where hrp and hz are 1, while h phi is rp. When you insert these values for h in the general equation, you get the expression for cylindrical coordinates. Let us do an example to demonstrate a line integral using polar coordinates. Let f of r be y. Let's integrate in the rp direction from 0 to r by letting rp of t simply be t and phi constant alpha. Let us plot this curve as the green line. As phi is a constant for this curve, the phi dt will be 0. In this case, rp is our parameterization t. Hence it's common to simply call it rp. The rp is 1 and can be removed. As we are integrating over rp and our limits are given in rp, we can insert them into the integral limits. Insert the function f. As we are integrating in polar coordinates, we need to express y in polar coordinates. Insert the value for phi. And solve the integral, which becomes rp squared over 2 times sine alpha. Then insert limits. And we have solved our first example. Let us do one more example with the same function, but change the curve to a constant radius. And let phi be our integration parameter. We let phi go between 0 and 2 pi, which will be a full circle. This may very well be the most common curve for line integrals in polar coordinates. This time, the r dt will be 0 as the radius is constant. As t is phi for our parameterization, we can keep phi as our integration variable. The phi is 1. As phi goes between 0 and 2 pi, we can write these as the integral limits. Insert the function f of r is y. And rewrite y to polar coordinates. Insert the value for rp. Let's add the unit vectors phi hat to the curve. Note that it varies along the curve. As we have a phi dependence in phi hat, this must be included. Hence, insert expression for phi hat in terms of x hat and y hat. Now we can split the integral into two integrals. Write the constants before the integral. This has primitive function minus cosinus phi squared over 2. As we get the same value when we insert the upper and lower limits, this integral will be 0. Write the constants before the integral. This has the following primitive function. Sinus 2 phi will evaluate to the same value for upper and lower limits, and therefore will be 0. And the integral becomes. Cancel the 2, and the integral becomes minus pi r squared in the x-hat direction. Note that pi r squared is the area of the circle. As our final scalar example, change function to x squared. Let RP be AT, where A is a constant. And let phi be BT, where B is a constant. We let t go between 0 and capital T. This will create a curve that looks like a spiral. This will illustrate the general case when we need the parameterization t. We have the two derivatives, the rp dt is a and the phi dt is b. Let's insert the rp dt and insert the phi dt. Then insert that the function is x squared. And rewrite x in terms of polar coordinates. As rp hat varies with phi, we need to rewrite it in terms of x hat and y hat to include the phi dependence. Same with phi hat. Then we would insert a parameterization for rp. And insert a parameterization for phi. As we have rewritten the integrals in terms of our parameter t, we can insert the limits for t here. This is how you would solve it if you have a general parameterization. I will not waste time and solve it here. I mainly wanted to show all the steps needed for the general case. But for most cases when we use polar coordinates, it's because we can integrate either in the radial direction or in the tangential direction, which was the two first examples I showed. Let us move to integrals over vector fields instead. Let v of r be ky x hat. Let the curve return to have a constant radius. And go back to our integral over a full circle. This time, however, I will offset the circle from origin. The new center is x0 and y0. We can also draw the vector field we are integrating as an arrow plot. We will do this example with the most common line integrals for vectors and use the dot product between v and ds. First, we must notice that our definition of polar coordinates require that the circle is centered around origin to give our simple parameterization of the curve. Hence, we must shift the coordinates to move the circle to origin. Define x prime as x minus x0 and y prime as y minus y0. This will shift the circle to the center if we use x prime and y prime on our axis in the figure. We can reorder this to get an expression for x and repeat for the y coordinate. Now, let's insert expression for the velocity v into our integral. And insert expression for the translation of the coordinate system. As the curve is in the phi direction, we can insert the phi part as ds. We can move the constants in front of the integral. By using the expression for phi hat, we can calculate our dot product with x hat. Then we can rewrite the y prime in polar coordinates, which is rp sinus phi. As we only integrate in the phi direction, we can insert these limits to the integral. Distribute sinus phi. this expression will have the following primitive function. Here, both these terms will cancel. We have input the limits 0 and 2 pi, and we are left with the following. Let the two cancel and simplify. This will be the end of the line integrals part. The main part is to learn how to rewrite them as ordinary one-dimensional integrals. If you learn that, you have understood the cylindrical coordinates part of this. Let us continue to area integrals, which we have in two-dimensional space. We can start by integrating a scalar function. In Cartesian coordinates, our area element will be a small rectangle with size dA equals dx times dy. We can therefore insert dx dy into the integral. The easiest limits are when we integrate the rectangular domain, here from xs and ys to xe and ye. Here we can write the double integral as two integrals, one for each direction, with constant limits on both. Then we can divide the rectangle into small regions of size dA and let the number of elements go to infinity. But what if our domain instead is a circle? We did show in the previous video that we can still do this one in Cartesian coordinates by using functions as limits. We can insert expressions in the inner integral. Here we go between minus square root of r squared minus x squared to plus the same expression. Now we can fill the circle with the rectangles and let the number of rectangles go to infinity. However, there are alternative ways of filling the circle with area elements. Consider the following. This is how the area elements will look when we use polar coordinates instead, and let the number go to infinity. Hence, let us remove the complicated Cartesian coordinate expressions and write it as an integral over rp and phi. Start by selecting all the radial elements for one step in the phi direction. When we integrate over these, it seems logical that the radial integral should go between 0 to the circle radius, r. In the phi direction, we know that to move around the circle, we go from 0 to 2 pi radians. Hence, write the integral from 0 to 2 pi. These limits should cover a whole circle, and are as easy as our rectangular limits in Cartesian coordinates. The question, however, is, how large is one area element when using polar coordinates? Let us select one area element. The distance in the radial direction will simply be the rp. Next, insert d phi into the figure. This means that the size in the tangential direction will be rp times d phi. And if we approximate the area element as a rectangle, we get that the area is rp times the rp d phi. When the rp and the phi goes to 0, it is good enough to approximate the area element as rectangular. Now we can insert the area element into the integral. And we have an expression for the double integral of a circle in polar coordinates. Let us demonstrate this with an example. Let f of r be x squared. Insert f of r into the integral. Rewrite x in polar coordinates. Expand. And combine. Start by solving the RP integral, which is a constant times RP cubed, and we'll have the following primitive function. Insert the limits and place the constants in front of the integral. This has the primitive function phi over 2 plus sinus 2 phi. Sinus 2 phi will be cancelled when we insert the limits and simplify the results. This is the answer to our example of an integral of a circle in polar coordinates. Let us consider a more general case. Let phi go between phi s and phi e, and r between rs and re. Now we can visualize what happens if we vary the values of these limits. Start by varying the upper limit for phi and the lower limit for phi. We can also vary the radial limits, start with the upper limit and the lower limit. These animations illustrated the shapes that we can create with polar coordinates with only constants as limits. It is likely that most of the times you do integrals in polar coordinates, it will be one of these cases. If we want to be more advanced though, it is allowed to have an expression as limits for the inner integral. Here I will illustrate it with a sinus function. So if you for some reason need to integrate over a domain that looks like this, it's possible in polar coordinates. We can add an expression to the lower limit as well. Note, this is just to demonstrate the concept. Let us return to our constant limits for the radial direction. If we swap the order of the integrals, we can modify phi instead. Let us demonstrate how an expression as a lower limit looks like for phi. We can do the same for the upper limit. The idea is that we can either modify the radial limits or the phi limits, but not both at the same time. Let's return to our normal limits again, which is the common case that we'll solve most of the time. With this, let us leave polar coordinates for a while and talk about general orthogonal coordinates. In the video about the double and triple integrals, we derived the general expression using variables u1 and u2. This general expression, which includes the determinant of the Jacobian matrix, does not require orthogonal coordinates. However, if we assume that our coordinates are orthogonal, there will be a much easier way of doing this. Let us first explain the general expression for the area element. When we take the partial derivative of the position with respect to our coordinates, we get one vector of each coordinate. These will create a parallelogram, which will be the area element. Its area is obtained from the determinant of the two vectors. The first row is the first vector. And the second row, the second vector. If we use the definition of the unit vector, we can rewrite the RDU1 as h1 times u1 hat. Similarly, the RDU2 is h2 times u2 hat. Now, let's add the condition that we have an orthogonal coordinate system, which means that these are orthogonal. This means that area element has become a rectangle. The area of a rectangle is the product of the length of the two sides. This gives us a much simpler expression that dA is h1 times h2 times du1 times du2. Hence, we can simply replace the determinant with h1, h2. If we compare it to our polar coordinates expression, h1 is hrp, which is 1, and h2 is h5, which is rp. Hence, we will recreate the value for polar coordinates if we insert h1 and h2 into this equation. To continue with triple integrals, also called volume integrals, we simply add one more direction. Start by drawing the three vectors that create the volume element. They will be given by h1 du1 u1 hat, h2 du2 u2 hat, and h3 du3 u3 hat respectively. Assuming orthogonal vectors, we get the volume by multiplying the length of the sides. And we can insert the general volume element. You can see that the volume element follows the same pattern as area element. Just add one more direction. As we are in 3D now, let us move to cylindrical coordinates. In cylindrical coordinates, we also have hz is 1. Rename 1 to rp, 2 to phi, and 3 to z to write the volume integral in cylindrical coordinates. Then insert the values for h to get the volume element. This is the volume element in cylindrical coordinates. It is relatively similar to area element, but we have included dz in the volume element. Let us do a visualization of what kind of volumes we can integrate by using cylindrical coordinates. Start by varying the inner radial value and the outer radius. Then vary the lower phi value and the upper value. The lower z value and the upper value. Of course, we are allowed to use expressions as the inner integral limits as well. And depending on which one you want to add an expression to, place it at the inner position. It will basically be the same as you saw in polar coordinates, but we can modify z as well. As I don't think you will be using these that much, let's move on. The final topic we'll talk about for integrals is surface integrals. Here we will only cover the basic case where one of the coordinates is a constant and the surface is created by the other two. We did learn in the surface integral video that we can describe the surface with two parameters. The integral in the general case is given by the following expression. Here, n hat ds is given by the cross product between the two vectors representing our directions times dui duj. I and j are different and represent 2 out of the 3 directions. Similar to the double integral, we have the two vectors given by the partial derivatives of the position vector. And the cross product gives us the area element with the direction in the normal of this surface. This is the first vector in the cross product. And this is the second. Again, we'll use our definition for the unit vector for orthogonal coordinate systems and write the first vector as hi dui ui hat. And the same for the second vector. Once again, we will use that this video is about orthogonal coordinate systems, which means that the vectors are orthogonal. The normal vector should be orthogonal to both, which then is in the third direction. Hence, we can write n hat ds as uk hat times the area element. I have added a plus minus on the direction, as the direction of the third vector will depend on the surface. To demonstrate, let's look at the ends of a cylinder. The normal vector is normally pointing outwards. Therefore, on the top surface, the normal is pointing up, and on the bottom surface is pointing down. Hence, you need to look at the surface to determine if it's plus or minus for the normal direction of the surface. For orthogonal systems, let us replace the cross product with our new simpler expression. For cylindrical coordinates, there will be 3 different cases depending on which of the 3 coordinates we keep constant. Start by setting z constant, which will be the end surfaces of the cylinder. Update the equation to put the normal vector in the z direction and integrate over rp and phi. Insert the values for our scaling factors h. Note that this is basically the area integral from polar coordinates, with z hat added as a direction. Let us visually demonstrate which surfaces you will get with this integral. We have our base surface. Here I've added the normal pointing up. By changing the constant z, we move the whole surface to a different elevation. Changing the start and end radius is the same as for polar coordinates. Changing the start and end value for phi is also same as for polar coordinates. Let's go back to the original equation. Now we're going to let phi be the constant. Update the equation to get the normal to be in the phi direction and integrate over rp and z. Insert the scaling factors h, which both are 1 in this case. Here I will also drop the plus minus, but we could of course consider cases with the normal in both directions. Let us visually illustrate the surfaces you will get here as well. The surface this time is basically a rectangle. If we change the phi value, we change in which plane we have the rectangle. We can also change the start and end radius. And the start and end value for z. Let us restore the original equation again. And consider the final case where rp is the constant. Put the normal in the radial direction and integrate over phi and z. Insert the scaling factors h. Let us visually illustrate this one as well. By changing the radial value, we change the radius for the lateral surface. We can also change the start and end points for the angle phi. And we can change the start and end point for z. Let us end with an example. Set f of r is y and assume that the surface has constant radius rp equals r. We let phi vary between 0 and 2 pi, which gives us the entire lateral surface of the cylinder. Let z go between 0 and L. We are integrating the lateral surface of a cylinder, and we will assume that the normal points outwards. Note that the normal vector will have different values depending on the position on the surface. This integral is very similar to when we calculate the force from hydrostatic pressure on a cylinder in fluid mechanics. Start by writing that phi goes between 0 and 2 pi, and z goes between 0 and L. Insert that the function is y, and rewrite y to cylindrical coordinates. We know that rp hat varies over the surface, hence we need to rewrite it in terms of x hat and y hat to include the phi dependence. This is very important to remember. If your unit vector varies over the surface, you must rewrite it in terms of unit vectors that are constant to solve this type of integrals. R hat is simply the x hat and y hat parts of R when we remove the length rp. Use that rp is R on the surface. This whole expression is a constant with respect to z, and we can simply multiply by the length of the interval. Distribute sinus phi. This expression has the following primitive function. Both these will become 0 when we integrate from 0 to 2 pi. Only phi over 2 remains. Simplify. And we get the final result, which is the volume of a cylinder in the y-hat direction. This will be the end of this video. Next up, we'll talk about derivatives. Thank you.